time to start. The next speaker is Jarkko Peltomäki, who will speak about initial non-repetitive complexity of regular episturmian words and so on.
Okay, thanks. So good to hear from you all, and I'm grateful to have this opportunity to present some of my recent results. So I'm going to talk about 4 related topics. So I'm going to tell you about intersets of episturmian words, and then about this initial non-repetitive complexity of these words, and how it relates to Diaphragmatic exponents. And finally, I have some applications or corollaries in number theory on irrationality exponents of real numbers. So this is more like a quick reminder of certain topics and introduction to certain themes and so on. So no proofs. And the setup would be as follows. So say this capital delta is some infinite word. I call it a directive word. And say it's over a D-letter alphabet. And I will write it in this multiplicative form. So the point is just that 2 consecutive x's here are always distinct letters, and then these exponents that group the same letters in one block are always at least 1. And this sequence of exponents here, it's called the sequence of partial quotients, because in the binary case it relates to some continued fractions. And I've chosen the word regular here for a certain type of directive words. Maybe not the best word, but I had to use something. So I will most of the time assume that delta is regular, and it means that if you forget the exponents from delta, then the word is of this form, meaning that it's periodic with period d, and the first d letters of this word are all distinct. And okay, so let me define regular episturmian words. So let delta be like it was. And then I have some recurrences to define a sequence of finite words, this sk. And it's easiest to look at an example. So this is the Fibonacci case, really. So let's pick this regular directive word. You can more or less skip these first 3 words. They just correspond to these 2 lines. They are just there to set up the initial values. But the point is that the sk is obtained by concatenating the 3 previous words you had in the sequence, when k is at least 3. And this corresponds to this line here, which basically says that to form this sk, you just pick your previous word sk minus 1, and then you just look at your sequence of partial quotients ak and repeat sk minus 1 that many times. And then you just repeat this for sk minus 2 and so on. And you do this for a total of d minus 1 times. So here d is 3, so you do it twice. Here just the exponents are always 1, so you don't have exponents for these. And then finally you just repeat this word, but only once. So in this way you get this sequence sk, and it's a sequence of standard words, or when you have more letters, you could say it's a sequence of generalized standard words associated with this delta. But anyway, this sequence sk has a limit. I will denote it by c delta, and that's a regular standard episturmian word with this directive word. And if you would like to talk about, tell what is a general regular episturmian word, it's just a word that has the same language as this standard word c delta. And you can view these as combinatorial generalizations of Sturmian words. Like if your delta is binary, then this will give you Sturmian words, this construction. And this class also includes all Fibonacci, Fibonacci words, and the usual suspects. So this is the word class of interest here. And yeah, just a remark that you don't really need regularity on this slide, but then you just need to use some other sort of definition instead of this recurrence to make everything work all right. And then another thing is a numeration system. So now that we have this sequence sk, I just set qk to be the length of the word sk. And so I get a sequence of integers, and I can view it as a numeration system so that I greedily just express each positive integer as a sum according to this sequence. Like in this example we had, then this qk sequence looks like this. It's the sequence of Fibonacci numbers. And then if you want to express 10, well, you just find largest number from this list, which doesn't exceed 10, it's 7. So you write 7, 3 remains, and then you just repeat this thing for the number 3, and you get an expression like this. And well, it's customary to write that the representation of 10 in this numeration system is 1101, meaning that I write these least significant digits first. And well, this is well, the binary case corresponds to this Ostrovsky numeration system. So this is a certain sort of generalized version of it. And now that we know this, I can state this theorem, which I find very interesting. So it's somewhat old result by Drobet, Chastain, and Pirillo. And it says the following. So you pick T to be your regular episturmian word with some directive word delta. And then the theorem says that you have a unique infinite word C1, C2, such that whenever you look at its prefix of length k, then it is an Ostrovsky expansion of some integer lk, and your word can be expressed as a shift, as a limit of shifts of this standard word. So this is the standard word corresponding to T, it has the same language. Capital T is the shift map, and this is just the integer sequence you get from this. So you can express your T as a limit like this. So this C1, C2 word is essentially like a right infinite Ostrovsky expansion. And this sequence, actually, I call it the intercept of T, because in the binary case, it coincides with the usual notion of intercept via some number theory. But the point here is that, I mean, a general point, not only related to stuff that's coming, but like I didn't know about this theorem until recently, and I find that maybe many people do not know about this. So like this proof suggests that if you want to understand a property of a general episturmian word T, then if you can understand it on the shifts of the standard word, maybe this limit procedure allows you to understand it on T also. So like this could be useful in some contexts. And what I'm going to present soon, it's also useful in. And also remark that, okay, I put the word regular here, but this also works in the general setting when you don't restrict this delta at all. Okay, and then maybe something that is not known for everyone is this initial non-repetitive complexity function. So let X just be any infinite word, then its initial non-repetitive complexity function, INRC of Xn, is defined with this formula, but really it just says that this INRC is the maximum number of factors of length n seen when X is read from left to right prior to the first repeated factor of length n. So you just take a window of length n and slide it along your word from left to right, and you stop when you see the first repeated factor, and the stopping point of this window tells what this number INRC is. And this was introduced in 2012 by Mothatu in some context that, I mean, he was interested in some entropy questions, and it was brought, you know, to our community by Nicholson and Rampersad in 2016. So they evaluated this function for, you know, the usual suspects, Thue-Morse, Fibonacci, Tribonacci, and the like. And recently, Medkova and others characterized this INRC function for standard episturmian words. And most importantly for this talk, Wojcik recently in his PhD thesis found a formula for this INRC for an arbitrary Sturmian word. So not only on, you know, standard Sturmian word, but any Sturmian word. And this formula involves this concept of intercept I just showed you. And what I did, I took Wojcik's ideas and generalized this to all regular episturmian words. So here I need this regularity assumption because it just makes life easier. So I guess you could do it in some sense without it, but it's super complicated. So this just makes life so much easier, and it's still quite a general result. I can show you the theorem here, or parts of it. So this is it. So basically what happens is that you pick your regular episturmian word with some directive word delta and intercept C1, C2. And then you would like to compute INRC for the length n. So you assume that your n is some interval ik. This interval is related to length of pi special factor. Some technical stuff you don't have to worry about. But basically what this says that if a certain condition like this, so this is an inequality concerning the intercept of t and the sequence of partial quotients. So if something like this holds, then this theorem basically says that this interval ik is split into certain segments. So this inequality defines the first segment. And this basically just says that INRC is constant on that segment. And then you have some other segment, another value, and you know, two more segments. And in case something different happens, you have more cases, like 5 cases, and case 4 has 3 subcases. So it's like a monster formula you don't want to read or prove. But now I think that some of you might agree that this INRC function is inherently interesting, but why bother if it leads to such complicated formulas? And my answer to this type of a question would be that, well, you can use it to determine Diophantine exponents of infinite words. So what's a Diophantine exponent? So let x be an infinite word, then its Diophantine exponent I denote by dio of x. And basically what you do is you look at prefixes of x of this form. So you have some initial segment u and then a power where this e now could be fractional. And you look at the ratio like this. And basically you just find the supremum of ratios you can find in this word. And that's your dio. And so maybe just a short remark how this relates to other known things. So, I mean, if you don't insist that this is a prefix and you set u to be empty, then if you would consider this ratio, it would be the critical exponent of x, right? So this is something, this d of x is certain combinatorial exponent that's smaller than the critical exponent, could be equal. And if then you would insist that this is a prefix of x, but you would let v to be empty, then this ratio would measure what sort of initial powers you have in your word. And that would be smaller than the dio of x. So it's some sort of an intermediate exponent between prefix exponent and the critical exponent. But the point here is that with this INRC function, you can actually compute this DO of x. So with this quite simple result, and it even helps that this INRC is non-decreasing, so makes it somewhat easier to handle. So this in principle allows you to compute DO of x if you know this function, but of course in practice it might not be so easy. And now for some of my results. So what I proved was that if t is a regular episturmian word, and now this regularity assumption is really needed. I believe it's true without it, but I cannot prove it. So the theorem says that this Diophantine exponent is infinite if and only if the sequence ak of partial quotients is unbounded. Sorry, not unbounded, but bounded. And this was proven for Sturmian words by Arantsevsky and Bugod like 10 years ago. So that would be a first result. And another result would state the following, that if t is a regular episturmian word with period d, so d was the number of distinct letters in the directive word, then it says that if d is equals 2, meaning if t is Sturmian, or lim sup of the sequence of partial quotients satisfies that it's at least 3, then the Diophantine exponent of t is greater than 2. And we will shortly see why this is an interesting fact. And this was, well, this is not really in print anywhere, but you can deduce this from Arantsevsky and Berthe and others for Sturmian words. And okay, these are the main results. Then you might wonder, like, this looks a bit strange. Like, is it really necessary? And I also showed that in some sense it is. So I proved these two results. So this first one states that if you let t to be the episturmian word with this directive word, so here the lim sup would be equal to 2, having this intersect, then with the monster formula I showed you before, with some effort you can prove that the Diophantine exponent of t is less than 2. And this latter theorem is of the same flavor. Here the directive word is such that the lim sup equals 1, and then you have a similar sort of result. So in a sense, the assumption that the lim sup is at least 3 is needed to conclude that the Diophantine exponent is at least 2. Okay, and then the final part of this talk would just tell that what are the corollaries of these two results I showed in number theory. So let x be an infinite word over an integer alphabet with at least 2 letters. And let psi of x to be the real number that has x as a fractional part. Now, you could pose a general question like, okay, supposing I know I have some combinatorial properties of this word x, what can I infer about the arithmetic properties of psi of x? And of course, there are hundreds of questions you could ask, but here I'm considering what we can say about the irrationality exponent of psi of x. And I will also remind you what an irrationality exponent is. So you pick your real number psi, and its irrationality exponent mu of psi. So it's a number, and you define it as follows. So basically, you look at rational numbers p over q and compare them with this psi in the following sense, that the denominator of p over q appears here, and rho is some real number. And you would like this inequality to have infinitely many solutions. And the rho is the largest number you can put here so that you have infinitely many rational solutions. So that's the irrationality exponent of the real number psi. And well, this quantity could also be infinite. And in this case, it's customary to say that psi is a Liouville number. So this is the definition, but how it, oh, and then some basic facts. So irrationality exponent equals 2 almost everywhere. And then it's less than 2 if and only if psi is rational. And if psi is an algebraic irrational, then it's also known by a very deep result of Roth that mu of psi is equals 2. Basically, this just says that if you could prove that the irrationality exponent of a number is greater than 2, then you know it's a transcendental number. And how this relates to what I talked about previously is this following nice result by Adamczewski, which says that the Diaphragmatic exponent of x is a lower bound for the irrationality exponent of this number psi of x. And the proof is not that hard actually. And the core idea is that you remember that in defining this DO, we looked at prefixes of this form. So you pick such a prefix and you extend it to this periodic word. And you see this periodic word, if you interpret it as a number, it's a rational number. So you just use these rational numbers you get like this in the definition of the irrationality exponent. Then you need to work out some details, compute something, but then you will in the end find this result. And yeah, this is a general result, of course, for general x, but here I will just show what happens with episturmian words. And this is the two corollaries for the results I proved on Diaphragmatic exponents of these regular episturmian words. So if T is a regular episturmian word with directed word delta, then this psi of T, this number, is a Liouville number if and only if this sequence AK of partial quotients is bounded. And for Sturmian words, this was proven by Komatsu in 1996. And then the other result I showed you earlier implies this one. So it says that if I have a regular episturmian word with period D, then if this word is Sturmian or it satisfies this Lim-Sup condition, then the irrationality exponent of psi of T is at least 2 or greater than 2 actually. And well, then it has some obvious implications like psi of T is a transcendental number, although this is not a new result because this follows from Bouguet and Adamczewski's nice result from 2007, stating basically that whenever T has low complexity, the corresponding number will be transcendental. But anyway, this shows that these numbers that come from these regular episturmian words are atypical. They belong in a set of measure 0. And okay, still have a bit of time left, so I will just make a remark about these two results. So you see that I could find some episturmian words where the Diaphragmatic exponent is less than 2. So this has the corollary that there exists episturmian words that have only finitely many square prefixes, which was a surprising result for me. I mean, if every episturmian word had infinitely many square prefixes, then this Dio of T would be at least 2, and it would contradict these two results. And for Sturmian words, we know that they always have infinitely many square prefixes, but already like in the 3-letter episturmian words and even in the 4-letter, I mean, this is the Fibonacci, a word in the Fibonacci subshift. Even in those cases, this fails to be true. This I found very interesting. But yeah, I guess that's it. I don't have anything else to say. Just that if you take a look at the slides, I've added some links. So if you want to read the papers and so on, you can click on the links. But right, that's it. So thanks.
Thank you. So are there any questions? So, yes.
Maybe I can ask one quick question. Is there some other interesting class of words that would be worth looking at next?
I don't know. Like, if you would like to have these results on irrationality exponents, then you would really need some, workable characterization for this INRC function. And basically the proof is utilizing Rossi graphs. And like we all know that the Rossi graphs of episturmian words are very simple. So I would look at words that have very simple Rossi graphs. Then you have some hope in characterizing this INRC function, and maybe then you could get some results on irrationality exponents. So that would be my suggestion.
Okay, there's a question in the chat, by the way. Have you determined the Diaphantian exponent for all Fibonacci words?
Yes, I have. And I forget. No. Yeah, I know what it is. So you take the critical exponent of the Fibonacci word and you subtract 1. So that would be the Diaphantine exponent in those cases.
Thank you again. And if there are no more questions, I just have a very short comment that if there is a paper, if your paper is about episturmian words and numeration systems, I have to read it and to understand better what you do. Because numeration systems, it's interesting.
Yeah, I would say that there is not that much about, general properties of numeration systems, but maybe this result is the interesting one. And my paper, I mean, this paper, of course, has a proof of this theorem, and but my paper also has some, in a way, different proof. So you can look at both.
Thank you. And if there are no more questions, then we have 2 minutes before the next talk. Thank you again.
So if there is time, I would like to ask a question.
Yes?
Gabriele Fici. Hi, Jarkko.
Hi.
It was about the abelian critical exponent. I don't know if it has been studied for episturmian words.
No, I don't think so.
So it would be a nice problem to study further, maybe.
Yeah. I mean, I would really like to know if the abelian critical exponent of Fibonacci word, if it's even positive, because it looks like if you compute it, with a computer, it looks like it tends to 0, but I don't know.
Okay, thanks.
Thank you.